Standard enthalpies. Let's look at a table of thermodynamic properties. And in particular, we're going to look at the column of numbers that's the enthalpy of formation of a compound from its elements, or the first column of numbers on our table. When we look at the delta H values, they're the values that accompany the formation of 1 mole of a compound from its elements with all substances in their standard states. So when we look closer at our table, it tells us that our delta H of formation is at standard state. That's what that degree sign tells us. The units are in kilojoules per mole. And when we look at all of the substances that are listed on the left-hand side, they're listed in alphabetical order, and they're listed in the state they would be in their standard states. The delta H of formation values tell us again how much energy is associated with the formation of 1 mole of a compound from its elements. Now look at silver, aluminum, and beryllium for a minute. All of those substances have a delta H of formation value of 0. And that should make sense because the enthalpy of formation is the energy associated with the formation of 1 mole of a compound from its elements. And silver, aluminum, and beryllium are elements. They're not being formed from elements. We also want to notice that these values are defined reference values. It's important for us to realize that we can only measure changes in enthalpy and not absolute values. So let's look at some examples of enthalpy of formation problems. When we deal with enthalpy of formation problems, they're always written so that the reactants are in their standard state and we have 1 mole of product on our product side. So here's an example. Let's say that we want to write the enthalpy of formation equation for aluminum oxide. Well, that means that the aluminum oxide is going to be a product and we're going to be forming it from its elements. So we'll write out our equation and balance it. We've got aluminum plus oxygen produces aluminum oxide. And if we remember our diatomic molecules, aluminum is a diatomic molecule, or aluminum is not a diatomic molecule where oxygen is. And then when we look at aluminum oxide, we know that aluminum is a +3, oxygen is a -2, so that's where that Al2O3 comes from. Now when we balance this equation, we're going to put a 4 in front of the aluminum, a 3 in front of the oxygen, and a 2 in front of the aluminum oxide. And notice that everything is in its standard state. Aluminum is a solid, oxygen is a gas, and aluminum oxide is a solid. The only issue with the way this is written is when we talk about the enthalpy of formation equations, they're the formation of 1 mole of a compound from its elements. And when we look at this particular example, we've got a 2 in front of our aluminum oxide. So we're going to have to divide all of our coefficients by 2. So our enthalpy of formation equation here would be 2Al plus 3/2 O2 gives us 1Al2O3. Now we've got the formation of 1 mole of a compound from its standard state elements. So here's another example. Let's say that we want to write the enthalpy of formation equation for C6H12O6, which is glucose. So we're going to form it, which means we're going to put it on the product side. We're going to form it from its elements, so carbon, hydrogen, and oxygen are going to be our reactants. So we've got carbon in the solid state reacting with hydrogen in the gaseous state, and oxygen in the gaseous state to form glucose, which is a solid. We remember that hydrogen and oxygen are diatomic molecules, carbon is not. And when we balance it, we get a 6, 6, 3, and 1 for our coefficients. And for this particular example, we've got a 1 in front of our product, so that's our enthalpy of formation equation, and we don't have to simplify it any further. So what if we wanted to find out the enthalpy of formation for a reaction? Let's use the combustion of methane as an example. And our first step would be to write out and balance the equation. So we know that a combustion reaction has some kind of fuel. In this case, it's methane. We're going to react it with oxygen, and we're going to produce carbon dioxide and water. So we write our balanced equation. We're going to need to put a 2 in front of the oxygen and a 2 in front of the water to get that equation balanced. All right, so once we look at this reaction, we need to consider the fact that we're forming carbon dioxide and water during the reaction, but we're breaking up methane and oxygen during the reaction. Now, our delta H of formation tables give us the values for forming compounds. So we can find out the carbon dioxide and water values right off the table. But the methane and oxygen aren't being formed, they're being broken down. And we know that from Hess's law, if we just reverse the reaction, we switch the sign on our delta H of formation value. So we can make that into an equation. And our equation is as follows. The enthalpy of reaction for a reaction equals the sum of the enthalpy of formation of our products, and we're going to have to multiply it by the number of moles of a product we have, minus the sum of the enthalpy of formation of our reactants, and again we're going to have to multiply the values on the table by the number of moles of each substance. So if we look at this particular example, we're going to need to come up with the sum of the enthalpy of formation of the product. So we're going to take 1 times the value of carbon dioxide off the table, which is negative 393.5, plus 2 times the enthalpy of formation value for liquid water on the table, which is negative 286. And we put that all together, and that'll give us the sum of the enthalpy of formation of our products. We're going to subtract from that 1 times the enthalpy of formation of methane, which is negative 75, plus 2 times the enthalpy of formation of oxygen, which is 0. So when we put those values into the calculator, we're going to get negative 965.5 as the sum of the enthalpy of formations of our products. And we're going to subtract from that negative 75, which is the sum of the enthalpy of formations for our reactants. That's going to give us a value of negative 890.5 kilojoules. The negative sign tells us that this particular reaction is exothermic, which makes sense because combustion reactions release energy. Now, once we calculate that delta H of formation value, we could then go through, plug that into the equation, and add stoichiometry to the problem.